Welcome, everyone. So this is first session after lunch, so I know it's a bit heavy now to comprehend and understand these topics, especially when we ask how many people here know about Ringbuffers. As you can see, there are a couple of keywords on the screen here. Probably you might be wondering what Ringbuffer is and how you can use it and take advantage in your Go application. But also we're looking at the real-time aspect of these type of applications. So what I'm planning to do today is, first of all, I would like to give you something in return. So basically, because you're attending this talk, I need to make sure that you leave this room with some experience you can use. It doesn't matter how much you know about Ringbuffers, or it doesn't matter how expert you are in Go applications. There is something for every one of you here in this talk. I usually focus on the deployment side, so putting your application into production. Most talks here today actually are really good talks. And in fact, most are focusing on various aspects of Go applications. So we want to make sure we take it next step, right? We want to level it up, and we want to add value to it. So my name is Fawaz Ghali. I work for a company called Hazelcast. I lead developer relations department, and I'm principal data architect at Hazelcast. Obviously, this solution I'm providing today is not limited to the demo I'm trying to achieve. So you can use it in exact domain or use case you already have, and I will show you how you can do it. Before we start, anyone can guess who are these guys on the screen? Say again. Beatles, yes, that's correct. So I'm based in Liverpool. I took a train back from Liverpool to London yesterday. So what I wanted is just whenever you hear real time or you hear stream processing, we're not talking only about music, so or TV streaming. Stream processing is essentially everywhere. And this type of applications where you try to do with or use real-time scenarios is essentially even for you as end user on your mobile apps as well. So streaming and stream processing are completely separate, and streaming is just part of the stream processing. Now, most use cases for Go applications focus on some kind of problem or use case. And essentially, your boss comes to you, asks you to develop some kind of solution, and they expect you to provide the solution as straightforward, right? So they give you a use case or a problem, and they look for a solution. And we all know that's not the case, especially if you take your Go application and try to move it from development into production. There are so many elements in this process, and obviously, when you want to make sure that it runs in production, you want also to handle various aspects. So part of this talk today is not related to Go or Ringbuffer. So like maybe 20 minutes or so, I want just to make sure that you understand what real-time is, and what stream processing is, and how you can take advantage of these type of solutions. And the second part is we're going to demonstrate how you can use it for Ringbuffer. So maybe it is you, maybe it is me. This is where we look at the perfect or best use case scenario for our application. So you have a limited number of transactions or limited number of events, and you try somehow to process it, right? So most of you, I would say maybe 90 to 95% of people attending this talk are dealing with some kind of batch data, which means you read data from source into your Go application, you store it into database or file system, and then you load it back into memory, and that's where Ringbuffers comes into place, obviously, and then you try to do some kind of visualization. It might work, and it can basically lead to some of what you expect in terms of results, accuracy, percentage, and so on. But we all know this is not the reality, right? So when you take it and put it into production, most applications fail, and simply because you want to handle so many elements and factors in this process. So for example, when it comes to deployment? What are criteria you use to deploy your Go application? How do you make sure you use the right CPU power or right memory size, for example? How many clusters you need, and how many nodes in each cluster? So many elements comes into place, and this is will make or break your application, right? Because if your application runs on, I don't know, maybe 1,000 transactions or 1,000 events, there is a high probability chance that it will fail if you give it 10 times more. So if you give it, for example, 10K events or 100K events, basically, we don't know how it's going to work. So to give you some definition, so we all agree what we're talking about today here, anyone can guess how long it takes for an eye to blink? Any guesses here? 500. Yep, so it's basically a bit faster on average, so 1/3 of second. So 500 or 350 milliseconds is how long it takes for an eye to blink. Now, if I ask you to go and write Go application to measure eye blinks in this room, you probably can get away with it. You probably can create these type of applications. But now, if I ask you to take the same application, I don't know, and run it in Liverpool station or somewhere downtown, basically it will fail. Why it will fail? Because, of course, number of transactions or number of links per second. And this is also same, you can see it for clap of hands, for example, or DSLRs. These actions are in sub-milliseconds. So this is exactly what we're talking about today. If you're dealing with batch data with your Go application and you handle or process data from yesterday or 1 week before, probably it's not the right approach, but at some point you need to shift your application now, which means you need to handle real-time events as well. I would say most applications on your mobile now use some kind of real-time stream processing, and especially with those who are expert in Go, know how hard it is to deploy real-time stream processing Go applications. Now, you might be wondering, why do you need to care? Why do you need to care about real-time applications? Simply because these change over time, right? So these days where you just handle data from database or file system are gone. If you haven't moved to real-time stream processing or real-time applications, you're probably missing out, especially if you're trying to advance in your career. You need to look at large companies. Obviously, this talk is being recorded, so I can't name companies. Feel free to grab me afterwards if you want to discuss it in more detailed use cases or specific names. And obviously, you look at it in everywhere, right? So you look at it, for example, bank and financial institutions. You see it in IoT devices, smart cars, for example. You see it in hospitals. You see it in sports, for example, those who follow football and know about VAR. You see it on screen, which is like it gives you hours or minutes and then seconds. That's not the case. It's actually sub-seconds, which means it's minutes, seconds, and sub-seconds. So that's how accurate it should be. Obviously, you see it in machine learning and AI. Now, to give you some kind of idea what we're talking about, let's just look at, for example, ATM, right? So you have a credit card or debit card. You're trying to get money out of it. So if I ask you to write this Go application, these are the most important or obvious steps. So you need to ingest the data. You need to read data from your card. You need to do some kind of data enrichment. You do some kind of transformation. Also, you do some kind of prediction in your Go application, and this is where the final response comes into place. So essentially, you swipe your card, you add your PIN code, this request goes to your bank, and then come back. Anyone can guess how long it takes for this operation to complete? Sorry? 500 milliseconds? Second? 150 milliseconds. So yeah, I mean, it's 150 and less, depending on the bank and if they have open bank or not. Usually, most banks here in the UK have SLA or time frame, which is around 40 to 50 milliseconds. So this is kind of like how fast you need for your Go application to process the data. Ringbuffer is part of this solution. So there is some hardware limitation, which means network hops how far your ATM from your bank and where your bank stored the data and so on. So the network hops, for example, or input-output, you can't do anything about it. What you can do is to enhance this in your Go application. Now we're going to deal with a JSON format, obviously, to read in your Go application. So for example, this is just a example here. So the JSON format here contains transaction number, for example, amount, merchant, where is this ATM located, device, if you, for example, using iPhone and so on, and geolocation or GPS coordinates. Now we want to enrich the data, right? We want to add into it. So for example, a credit score attached to my account, perhaps gender, age, and so on. And as well, we need to do some kind of transformation. So this is kind of like feature engineering for your Go application. If you're working in machine learning, you probably understand what I'm talking about. If you don't work with machine learning or data analytics, essentially you get a table or set of features, and you need to decide which of these features you should use for your application. And then you need to come up with the solution. Most solutions we focus on for real-time analytics are machine learning based. You don't have to. You can use if-else statement in Go. And then this is where you get the response, right? So probably it took me a couple of minutes to explain it. Obviously, we're not talking about minutes, as I mentioned. We're talking about sub-milliseconds here. And this is where we need not only to process data, but also to actually be able to provide response. And not only the response, but also to avoid any false positive in this process. So anyone wants to guess what is false positive in this case for fraud detection? Go on. Exactly. So So exactly, so essentially it is you who's using your card, but for some reason your bank decides to decline this operation and flag it as a fraud. Obviously, banks lose money when you don't do transactions, which means you need to minimize false positives. So if you have, for example, 2 bank accounts, you're probably going to use the one which has most fast response time and most user experience, better user experience as well. Now, hopefully now you can understand what we're talking about in terms of real-time Go applications. Essentially, you need to combine between 2 different types of data. Again, most of us here in this room have some kind of batch or historical data. This is data stored in database. So we're not talking about this type of data today only, but we're talking about the real-time data, which means events are coming in this very moment, and we want to make sure we process it before we store it into database. Let me say it again. We want to process the data before we store it into the database. So this is very crucial to understand, and obviously Go applications, in order to be able to run a real-time, high-performance stream processing, we need to be able to combine between these 2 different types of data. To give you some examples, what does it mean? So the features you see it on greens, or attributes, if you want to call it, if you don't work with machine learning, are the pre-compute features. So these are static or batch features. We have also the real-time features. So these features change over time. For example, how much money you're trying to do for this transaction, how far from your home, for example, and number of foreign transactions, which is kind of like real-time or near real-time. And now, we're talking about number of events which is hard to comprehend in terms of how many transactions per second. So for some of you, you might be able to process 1,000 transactions or events per hour or per day or per week, it depends. But here we're talking about billion transactions per second. So this is where you need to provide alerts, you need to provide some kind of trends, and you do data enrichment. Now, I wanted to explain what you need for these type of applications. So usually you end up with 2 types of solutions. So one is data streaming. So for example, who heard of Kafka or who uses Kafka with their Go applications? Good. So Kafka is really good in terms of data streaming. So essentially you use it to transfer or transport data. But at some point, you want to be able to process the data, and at the same time, you have the fast data store where the ring buffer comes into place, which is kind of like the fast data store. So you want basically to combine two tools at the same time. Now, I work for a company called Hazelcast, so it's open source. This demo today and Ringbuffers, you should be able to download the source code and run it alongside your Go application. I don't want you to change anything in your Go application. I want you to keep it as is, and I will explain what you need in terms of integrating Ringbuffer into your Go application. As you see it here on far left, you see multiple sources. I would assume most of you use one single source, maybe more, but we're talking about multiple data sources. We need to be able to read or ingest data from multiple sources, and then we should be able to do the stream processing, which means we process the data before we store it into the database, and we load it into memory, into a ring buffer or map or list, and so on. Obviously, if you are a data scientist or work with machine learning, you can use SQL. But today, we're talking Go, right? We're talking Go, so you can use the Go client in order to connect your application. And this will allow you to use all these features we're talking about today. Once you're happy with the results, obviously, you can output it and provide some kind of alerts, or you can send it back to Kafka, or even send it to WebSockets. Now, if you already have a Go application, you probably have some kind of output. So I don't know, maybe you send it to some kind of API or WebSockets. But if I ask you now to change it and have external sync or external outsource, you probably need a few days or a few weeks to be able to integrate it with your Go application. And that's not the case we're talking about today. So this is basically 2 or 3 lines of code. You should be able to connect it to multiple syncs or multiple outputs. Now, the cool thing about it is how to scale. Now, every time I mention scaling, some people here, or anywhere basically, assume we're talking about scaling data, and some assume we're talking about scaling compute or performance or functionality. And the right answer is a combination between two. Essentially, you want to make sure your data and your compute are stored as close as possible. Which means it should be partition aware. So if you have multiple data centers, so if you have a data center here in London, for example, and data center in Germany, for example, you want to make sure your Go application, of course, microservice, we're talking about microservice today, is stored as close as possible to where your data source is. This is very important because we're trying to minimize latency here. Obviously, now we're talking about how we can connect it into Go infrastructure. So I'm going to show you now and flip into the Go just to show you how you can achieve it. But then we will drill down in each of these aspects. So don't get discouraged if you see this code. Essentially, it's just a way of connecting your Go application and to Hazelcast, and then I will show you how you can implement a ring buffer and why you need to implement ring buffer. So this is just a simple example. Essentially what it says I want to connect my Go application to Hazelcast. Obviously, in our case, we're going to use the ring buffer. But every time we start a new client, essentially we start a new node in our cluster. So those who don't work in DevOps and want just to make sure they understand the process, in simple terms, you have a cluster, and in this cluster, you have multiple nodes. So every time you run a new instance, essentially you end up with a new node in your cluster. Now, if you have, for example, map, you can store it as key value pair. So this is just simple terms. I will explain what ring buffer again. After this, I just want you to understand how you can connect your Go application into Hazelcast and should be able to use the stream processing capabilities and run it in real time. Now, obviously, with this type of applications, we need to focus on why we need ring buffer. So who here deals or have interacted with ring buffer in their applications? Show me your hands. So not many. Right, so ring buffer essentially it's memory structure. So let me explain what it does. It can be replicated. So like I mentioned, we're talking about large scale applications. So we're not talking about simple standalone application anymore now. So we're talking about distributed application. And we want to use this memory structure and make sure that it can be replicated. It's not partitioned, which means you can't split the content of ring buffer. Ring buffer is essentially, as it says, it's like a ring, and it has a limited size, right? It's like array, but this array is like a circle. So it has a tail and end, tail and head. So the tail and head essentially it tells you where you need to add your data into the ring buffer and where you can consume it. And obviously, whenever you have multiple clients connected, it can be treated independently to actually read items from the ring buffer. And this is very important because it tells you exactly where you need to stop and obviously where you need to continue, as I will show you if failover happens in your application. So in simple terms, ring buffers are memory structures. If you have a ring buffer in your application, essentially it's an array, but it's like a circle, obviously. So it has limited capacity or limited size. It has tail and head, and this is where you actually decide where you need to insert data, and of course overwrite data because it has limited size, and where you can consume it as well. Now, ring buffers in general are good for microservices. Simple reason for this is because microservices are good for distributed architecture. So who uses microservices in their Go applications here? Good. So essentially, microservices are, in simple terms, like you split your code into smaller pieces. This is in simple terms. Of course, it's easier to deploy if you have multiple clusters and multiple nodes. You can deploy multiple microservices services on different cluster nodes. Obviously, it's easier to maintain, so you can actually have one enabled, one disabled between microservices. And of course, it's easier if you want to track performance or if you want to actually do some kind of stream processing. So in simple terms, if you have a Go application on the left side and you want to transfer it into microservice architecture, you actually can split it into multiple tasks, and from there you can connect it to multiple topics in Kafka. So multiple topics, you can, for example, use something called DAG format. So DAG format allows you to connect different type or different pieces of your code at the same time. So you don't need to replicate or read multiple times, for example, from one source. You can read from one side, do some kind of processing, and do at the same time visualization or attach it to different microservice. If you're dealing with Kafka, you can attach different microservices to different topics. And this is where the ring buffers comes into place. This one here. So this is where ring buffer comes into play. So you actually have some kind of data objects in memory, and you can use the ring buffer in order to be able to access data in faster way and minimize latency. So now let's just discuss an example here and how you can achieve it. So I'm going to use microservices architecture. You don't have to. Obviously, it becomes easier when it comes to put your application into production. So if in my case, I'm using ring buffer from Hazelcast, and I have 3 microservices. So I have publisher, which sends events. And then I have logger, which actually logs every single message. And then I have alerts, which is like sending alerts on specific condition. So all these are connected to one single ring buffer. Now, in order to define ring buffer here, what you need is first to start a new Hazelcast instance. This will allow you to run a cluster. And from this cluster, you actually have one node. Now, if you want to add more nodes to your cluster, you just simply repeat step number 1 or line number 1. And from there, you can actually get the ring buffer. Again, ring buffer is memory structure. and it tells me I want to store data in memory, and this data structure is actually replicated. So all nodes, different nodes, will have the same access for the same ring buffer, but it's not partitioned, so it's not actually split into multiple nodes in different parts. So this is how you define the ring buffer. So which means in your application, you don't need to change the structure, right? You just need to create a new microservice, and from this microservice, you can actually call a ring buffer. Now let's just look how the publisher works. So remember what we're trying to do here. We're trying to send events from one microservice to my ring buffer. So here I'm just saying I want to send this message. Obviously, it depends how much you want to send to alerts. So I'm just specifying, for example, 10% to be sent to alerts, and the rest will go to logger. And what you need to look at is line number 14. So this is where I'm trying to add this sequence into the ring buffer. And obviously, I'm just doing sleep here. And this sleep command is just to make sure it's easier for you to read it, right? It's just actually delay the, execution time. So if you run it into production, you need to delete this line here. Now for the logger, essentially, it takes this ring buffer and it read once, right? So this is a message where every time you send message from publisher to your ring buffer, we have a logger microservice on alert actually, and it receives each of these messages. And the alerter is just for 10%. So every time you have a string or a message which starts with alerts, obviously, I want to make sure I actually read it or send it to user. In this case, obviously, we're just having a limit on as 10%. Now, this is great, and it works really well on your machine, but obviously nobody put production code on their machine. So my recommendation for this type of applications, especially if you work with ring buffer and large-scale applications, is to store it into cloud. It doesn't matter which cloud provider you use, but it's very important to be able to load this data into cloud. For example, as I mentioned, if you have multiple data centers and you have multiple Go microservices, you want to make sure to store all data into the cloud. Obviously, you spend some time on, sending data into the cloud, but as soon as your data in the cloud, basically the application will perform or outperform any applications or any microservices run locally. Now, in order to run it into the cloud, what you need is kind of like some kind of, setup. So it depends which cloud provider you use. So you define your cluster, so where your cluster is hosted. Of course, if you have, for example, token attached to it, so security code or security, it's like, username, password in simple terms. And obviously, you need to define logger to be able to log any error messages. And from here, you can see I define the key value for my solution. I'm using a cloud solution based on Hazelcast, but you don't have to. And this will allow you to actually connect to the cloud, define the ring buffer over there, and then basically send, if you have publisher or more microservice, send it all data, all events into one center place. Now, let me ask you, what happens if your application crash? What do you do usually? Usually you just stop the application and rerun it, right? So this is fine, again, for development and small applications. But if you work with a real-time application, it doesn't work this way. It's not right, because usually you lose some kind of data. Now, the question becomes, how do I make sure my data in my ring buffer stays when there is a failover, right? How can I make sure if there is a kind of disaster or crash, whether it's a software crash or hardware crash, the data in memory is stored in specific state, so that when I relaunch my application, I continue where I stopped. So there is a solution for it, and this solution essentially is a failover solution, which means you have to create two different nodes or two different clusters, first of all. And these two clusters essentially allows you to run something called blue-green architecture. So the blue you send it to end users, and you have the green running in background. And every time you want to do some kind of maintenance, you can send the green to the front and take the blue to the back, and you do your maintenance or change your code, whatever you want to do. And this will make sure you have a high availability for end users. And the high availability, we are moving from 4 nines to 5 nines, which is 99.99 to 99.999. So this is how accurate and how available these applications should be. So you define two clusters and you run code. I will show you the code now, so you can use it for your Go application. And you send some data for client 1 or cluster 1. Now we want to stop this for whatever reason, so we can try to stop it manually, and the second cluster will just pick up where the first cluster stops. So if you have a Ringbuffer application or Ringbuffer Go application, you need to make sure you deploy it into two clusters, so exactly the same application. And this will allow two clusters to access the same Ringbuffer. And if for whatever reason one cluster fails, you can take the data and actually complete or continue processing in cluster number 2. Now, how can you do it in Go? So here you can see I'm defining the failover. So essentially, I'm just creating a map key value. You can use Ringbuffer as the same thing for same structure. So this code allows me to create some events, and these events essentially will check whenever you want to call or read the data from your memory structure. So the map key value essentially is similar to Ringbuffer, but obviously with unlimited size. So it depends on how much memory you have, obviously, with your application. And this will allow me to check where I am processed. So for example, it actually have a pointer exactly where the read process is in my Ringbuffer. So if for whatever reason cluster 1 fails, I can pick it up and continue in cluster 2. Now, very important topic when you deal with Ringbuffer is serialization, because you don't want to actually just store simple types in your Ringbuffer, right? So sometimes you need to have a complex structures, for example, in your Ringbuffer, right? So those who have worked with like complex structure know how hard it is to do serialization. And this is very important to actually do it if you want to deal with the Ringbuffer structure in memory, because you want to make sure to serialize data first. Then you store it into Ringbuffer. So as soon as you read data, you need to do deserialization. And if we look at performance, you can see why some applications take maybe minutes to run every time you want to launch it, and other applications can take few seconds simply because they do serialization in a wrong way. So let me explain how you can do it. So here you can see I have a city structure. So it has a city, country, and population. And essentially, you want to do a serialization. In this case, of course, I'm using the Hazelcast serialization. If you're not using Hazelcast for Ringbuffer, you need to make sure you use some kind of framework to do serialization. Don't just put the structure as it is in your Ringbuffer. It will work, but performance-wise, it's bad practice. So the good practice is to do serialization whenever you want to write, and same thing whenever you want to read. So if you look at the read-write code here, obviously you want to make sure you actually collect this structure. So in my case, I'm using city serializer in order to define the type of my structure. And from here, you can see I actually define right string, for example, if I'm using a string type or integer type, and how big the integer is. So this is very important, as I mentioned, if you want to work with complex structures into your ring buffer. So ring buffer not only meant for simple types, but also for structure types as well. Now, once you're happy with this, you can proceed to actually create some kind of structure into memory. Now, of course, when you deal with mapping, for example, for ring buffer, you need to make sure you store this into some kind of a ring buffer structure, and usually you need to define, you need to let your application know what you have in your structure. So in my case, I'm defining country, city as varchar, population as integer, and from here it's possible to store the data in memory. Obviously, when we deal with like large number of events, we need to make sure we're able to read this data not only through Go, for example, but also to use some other languages as well. So you can connect your Go application to SQL, for example, and SQL allows you to run advanced analytics on the same structure. So imagine you have a ring buffer structure in your Go application, and at the same time you want data engineers or other teams to be able to access this ring buffer structure and its data. You can use SQL to do so, and you can use actually SQL within your Go code. So as you see it here on the screen, and this will allow you to define what you want. So for example, if I add data into my queries here, so I'm using SQL inside Go, and this will allow me to add data. And obviously, with real-time data and batch data, so you need to be aware you're handling two different types of data at different speed, and these two different types of data are actually happening at the same moment. So this is where you kind of like look at ring buffer not only for as fast data store, but also for stream processing as well. And from here, you can actually proceed to do some kind of query. For example, you define the Hazelcast instance. This will allow you to create the mapping, and then you can do insert into your ring buffer. And from here, you can also populate it and fetch some data here. So for example, give me all data from my database. And if you run it, basically, so this is not SQL code, so this is SQL outcome, obviously, but it was written in Go. And this allows you to actually query your ring buffer in your Go application. So hopefully this gives you a flavor what you can do. And obviously, at this point, you might be wondering how you can connect your Go application and add ring buffer. In simple terms, ring buffer are good to actually have fast data store or fast data access, but of course they are limited how much data you can store in it. The best practices are to make sure to deploy it on multiple nodes, and this multiple nodes should be replicated aware, which means all nodes should have access to the same ring buffer structure. So this is one step. Second step is to be able to host it or run it into the cloud, so you don't end up running your Go application with ring buffer locally. You need to be able to run it on the cloud. This will allow you to have multiple microservices accessing this data at the same time. And the final step is to be able to do some kind of SQL on top of your ring buffer. So this allows you to query your data in different team or from different team or different ways compared to just the Go application. Now, this is not for everyone, obviously, but it is a very advanced and very well known or very trendy topic these days, because most companies are moving towards real-time applications. So if you log into some kind of apps on your mobile and you try at the same time to log in to the same app on your laptop, even it is you on your profile accessing the same account, you get different feed. Why do you get different feed? Because they run different code on laptop compared to mobile. And even though they use similar map structure, so for example, similar ring buffer, but what they do is they change the code, which runs basically in completely different way on your mobile compared to your application. Now, these applications are not meant for 1,000 transaction or 10,000. You can run ring buffer with 1,000, 10,000. That's not big deal. Or in fact, you can use different structures, but ring buffers are meant to be used for large-scale applications. So we're talking about millions of events per second, or in some use cases, billions. So billions transactions per second is what we're looking for here. And obviously, you need to configure. So by default, the configuration is based on how much data you can store in your ring buffer. But obviously, you can change configuration. If you are interested in most advanced or advanced use cases for ring buffer, come grab me afterwards. I can explain based on your use case. So finally, feel free to join a community Slack to ask questions about ring buffer or anything related to Go applications or anything related to real-time stream processing. So take a screenshot of this. It's open source, which means you should be able to download and try it in your Go application. If you have any performance issues in your Go application, come speak to me. You don't have to use ring buffer. We can definitely talk about or discuss how you can speed up your Go application. Again, it's not related to Hazelcast. It's not related to stream processing. It could be simply you're using different caching solution or different fast data storage. So we just need to make sure you have set up correct. So if you're interested in these topics, come grab me after this session. With that being said, thanks very much for attending, and I'm open for questions. Thank you.